Okay, so welcome to the NOC 23 MA03 Linear Algebra course. So my name is Joydeep Singh. I am TAing this course. So tutorial will be each week on Friday from 6 to 8 as informed earlier. So I will solve the means this linear algebra NOC is the rerun course. So I will solve the assignment from the previous run course which was run previously, and the means this year assignments will be similar look like the previous year. So I will solve the previous year, then you can do the your assignment of this year. You will get the idea how to solve the assignments, right? Okay, so let's start with the assignment 1 today. Okay, let me share the screen. What session to timing has been we written the same is no, there are means there are three tutor for this course. So all of you, anyone can join in any tutorial. So all three will be doing the same last year assignment. So whatever you will like, you can join whichever time it's convenient for you. So today there is at the same time from 6 to 8 there will be two tutorial and one is another, I think, right? Any problem? Okay, so let me start. Can you see the question assignment 1? Okay, so let me remove from here. Okay, so this is the assignment 1 for linear algebra. If you have any doubt, you can stop me and ask question. Yes, okay. So what is saying in this assignment, we will always denote R, the field of real numbers. So this is the, all this was done in the lectures. So the MNR, what is saying? It is the vector space of all n cross n matrices over R. So MNR, what it is? It is the n cross n matrices set of all. So in the lectures it was proved that this forms a vector space. What are the operation here? Two operation plus addition and scalar multiplication we have to define. So how we have defined the additions? This is the coordinate wise addition, right? So suppose for 2 cross 2 matrices, suppose for M to R, how you will define the addition? So this is yes, addition and scalar multiplication, yes. So that we have to define. So how the addition of two scalar matrices is defined: A1, B1, C1, D1, and these two A2, B2, C2, D2. How we will define the addition? By coordinate wise. This is the first A11 entry. So we add A1 with A2, B1 with B2, C1 with C2, and D1 with D2. So this is the our addition. This we define. So this is the addition, and what is the scalar multiplication? For any real number, suppose this is what R for any real number, we define R times A, B, C, D. What is this? Coordinate wise multiplication. R times A, R times B, R times C, R times D. So these two operations, this is the addition and this is the scalar multiplication. With these two operations, M2R, here M2R become a vector space. So similarly for n cross n matrices, you define the coordinate wise addition and scalar multiplication coordinate wise. Then MNR become vector space. So this become vector space over R. Field is the R, right? And now next is saying that PNR for the polynomials of degree less than n or less than or equal to n with coefficients in R. This is also forms the vector space. It was also done in the lectures. So this is the first one. And the second one, what is saying? PNR. What is PNR? Sorry. What is PNR? Set of all polynomials of degree, yes, of degree less than or equals to n. This also forms a vector space. What are the operation here? What are the addition and scalar multiplication? Here with coefficients in R. With coefficients in R. So suppose this is a polynomial a naught plus a1 x plus a2x square plus dot dot. Suppose this is p1x dot 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 plus an x to the power n, and p2 another polynomial. What is it? Suppose this is b naught plus b1x plus b3 x square plus dot 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 bn x to the power n. So then how you will define the addition? P1 plus P2 of x. What is the definition? What happened? P1 plus P2 of x. What is the addition? We will define the a naught plus b naught plus a1 plus b1 times x plus dot 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 plus an plus bn times x to the power n. This we will these are addition of two polynomial in PNR. And what is the scalar multiplication? For some c in real number, what is the c times p1 of x multiply c by each coefficient, where this ai and bi are all real number for I equals to 1 to n. c times just a naught plus a1x plus dot dot an x to the power n. So it will be c a naught plus c a1 x plus dot 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 c a n n. So these are the two operations. This is the addition and this one is the scalar multiplication. So with these two operations, PNR become the vector space over R. This also was done in the lectures. PNR becomes vector space over R, right? So these two are the vector space PNR and MNR. Okay. Now come to the first question. What it is saying? Consider the vector set V equals to R plus. What is R plus? R plus is the positive real numbers. All such x in R such that x is greater than 0. Set of all positive numbers. This is our set. Now we have defined. So this is the set. What is the set? V. This is R plus. Means set of all real number such that x is positive, greater than 0. So this is the set. Now we have defined two operations. So we have to check that means we want to make B as a vector space. So you have to define the addition and scalar multiplication. So here in the question they have defined two operations and we have to check. So how the addition is defined over B? So addition is defined. Suppose take two numbers u and v from small u and small v from b. How to define this addition? U plus b is defined like u dot b. This is the usual multiplication in R. Usual multiplication. Usual multiplication. Usual multiplication, right? In R. And so we have defined the addition. Now we have to define the scalar multiplication. So for any R, how you define the scalar multiplication? So you have defined the scalar multiplication A dot U, where U is from V. We define this. So these two are, so U dot B, how you define it? U to the power A, right? Because U is positive, so this is well defined. So you can take any power, U to the power A, right? As U is from B means it's the positive real number, U to the power A is well defined. So we have defined scalar multiplication by A dot U equals to U to the power A. So these two are our definition. This is the addition and this is the scalar multiplication. Okay, now you have to check that with this definition, is the V become vector space or not? So first, what is the question? It's saying that, first question, is V closed under scalar multiplication? So what do you think? Is V closed under scalar multiplication? Means what you have to check? Means you have to check if A is in R and U is in V, means R plus positive real number, then A dot U should in V equals to R plus or not, that you have to check. So what is the definition for A dot U? A dot U is the U to the power A, right? And U is positive. Yes. So you have to check U to the power A is positive or not for all A. All A in real number and U is positive. Right? So this, if U is positive and for all real number, you know that U to the power A is always positive, right? So as U is greater than 0, which imply U to the power A is greater than 0 for all A in real number, right? So U to the power A, which imply U to the power A belongs to V or the positive real number, right? Which imply A dot U is in V. So means for any A and U is in B, A dot U is also in B. So what is the meaning of this? Means B is closed under, so which imply B is closed under scalar multiplication. So what is the question? Is B closed under scalar multiplication? So what we have got? It's yes, right? Is this fine? The first one? Okay, fine. Okay. So now let's move to the next one. Question number 2. So the question number 2, this is the same first one. B is the same set of positive real number and addition and scalar multiplication are the as previous. Okay. So with this, what he is saying that which of the properties in the definition of the vector space which are given in the lectures are satisfied by B with this operation. You have to check B. What is B? This is the R plus set of all x in R such that x is greater than 0. And what are the addition? U plus B. It's U dot B. And what is A dot U? Is U to the power A. So these are the two operations. You have to check which are the properties satisfied by B. First it is saying that commutativity. So we have to check is these two operations are commutative or not. Yes. Property 1, yeah. So we will check. So first one, commutativity. What is the commutativity? First property, commutativity. So what is the commutativity for addition, right? So you have to check u plus v equals to v plus u or not, right? So this we have to check. So what is the u plus v? It's u plus v is, how is addition is defined? U dot v, right? And what is this dot? This is the usual multiplication in the real number. We know that two multiplication is commutative for real number, right? So this is same as b dot u. This we know, right? So this follows from the let me write as usual multiplication in real number in R is commutative. So that's why u dot v equals to v dot u. And what is v dot v plus u? This is by definition v dot u, right? So what we have got? So this is the same, right? These two. So we get u plus v equals to v plus u, right? So means this addition is commutative. So the first option is correct, right? Property 1 is satisfied. The addition is commutative, right? Okay. Now you have to check the associativity. Associativity you have to check. So what is the definition? Associativity. Question number 2. So associativity. So what is the definition of associativity? For u, v and w in v, you have to check u plus v plus w equals to u plus v plus w or not. This you have to check. So let's check. Yes. So what is u plus v plus w? U plus v plus w. Let's compute the left hand side. So u plus v first compute. What is u plus v? It's u dot v, right? Plus w. And then what is the So this is the one number u dot v plus w. Now what is the addition again? So this is u dot v dot w, right? So this we get. And what is u plus v dot w? U plus v plus w. So this is u plus v plus w, it will be multiplication, usual multiplication, right? How it is defined, addition. And then u plus v dot w means u dot v dot w. So now we have to check these two is same or not. But all these dots are the usual multiplication on r. And we know r is associative. Usual multiplication on r is associative, as usual multiplication on r is associative, right? Means what is this? Associative multiplication means this is, we know this is true for r, u dot v dot w. So this we know. So which imply the addition is associative, right? Which imply u plus v plus w is u plus v plus w. So the property 2 is also satisfied. So this is also associative, the addition. Now you have to check the, what is the next one? You have to check existence of multiplicative identity. So what is the definition for multiplicative identity? What we have to check? For u in r, we have to check does there exist a c in r, u in r plus or v. Does there exist a c real number such that u dot c dot u is u? So this is the multiplicative identity. So does there exist a multiplicative identity for v or not? So what will be the multiplicative identity? Can you guess for v? So what will be this c? 1, right? 1 will be the multiplication identity. So what is this? So if you take 1 dot u, means 1 dot u, how it is defined the dot? So u to the power 1, right? Means this is u. So we get 1 dot u is u, which imply 1 is the multiplicative identity. Right? Okay, so what we get? Option number 3 is also correct. Now you have to check the distributivity. Distributivity. What is this? Distributivity. What is this? So this we have to check means for a in r and u and v in v, which is r plus, we have to check a dot u plus v, it's a dot u plus a dot v or not. This we have to check, right? So let's check. So first write down what is the definition. A left hand side, u plus v. So what is the addition here? A dot u dot v, right? And now what is the scalar multiplication here? It's the it will become the power, right? So u dot v to the power a. right? So this is the scalar multiplication here. And now what is the left hand side? A dot u plus a dot b. What is this? So it is u to the power a plus b to the power u a, right? And now what is this to addition? So what is the addition here? This is the multiplication, right? U to the power a times b to the power. Now you have to check these two are same or not. But we know for real number these two are same, right? So as u dot b to the power a is equals to u to the power a b to the power a, which imply a dot u plus b is same as a dot u plus a dot b, right? So what we got? That these two operators are distributive, right? So this option is also correct, right? Okay, so what is the next one? Multiplication is linear, that you have to check. Multiplication is linear or not? Yes. Can we write a dot u plus a dot b? How you have written it? Why it will be a square plus ub? It is not a square, right? A dot u is u to the power a. Yes. Did you get? Nemesis? It's not the same. Yeah, that you can write, but a dot u, what is the a dot u? Yeah, that you can write. Yeah, you are, that you can also do. What is saying? He is saying a dot u plus a dot b. So first he is doing the addition. So it's mean a dot u dot a dot b. But here the multiplication is not. So here what is this multiplication? This is the usual multiplication, but this multiplication is not usual, right? Not usual. This is the usual multiplication, and this is also not usual. So what will be this? A dot u is u to the power a, and now this is usual multiplication, again b to the power a. So what you get? U to the power a dot b to the power a, right? So this is, we get the same, right? Okay, fine. What about the right distributive property? Okay, that you can also check. So what is this? What is the definition there? Means these two are commutative, right? We have checked that this operation is commutative. So it is also right distributive, right? Yes. Okay, fine. Okay, now what is the next one? Multiplication is linear. So what is the definition? Multiplication is linear. Multiplication is linear. So how we define the, so what it means, what we have to check for a and b in real number and u in b, which is r plus, you have to check a plus b dot u is a dot u plus a b, sorry, this is b dot u or not, this we have to check. So this is the multiplication is linear. So let's check the left hand side. What is a plus b dot u? So here the addition is the scalar addition. This is, and this multiplication is the what we have defined. So what is this? U to the power a plus b, right? So what is this? U to the power a into u to the power b. Now check this side. What is this? a dot u plus b dot u. So what is a dot u here? It's u to the power a plus u to the power b. And what is the addition here? For two vectors, we have defined how we have by the multiplication, right? U to the power a, u to the power b. So now these two become the same, right? So these two are same. So we get, which imply a plus b dot u equals to a dot u plus b dot u, right? So the multiplication is linear. So last option is also correct. So all the options are correct in question number 2. Is this fine? Yeah, okay. So let's move to the next one. Question number 3. So you have to check now, is V vector space over R? So you have checked few properties. So now you have to check, is V vector space? Is V vector space satisfy all the properties or not? So what do you think? Is V vector space or not? U dot u plus v, we have defined u dot v. In scalar multiplication we have defined u to the power a. Is V vector space? So what are all the properties? We have checked. First one, commutativity, we have checked. Commutativity. This was done. It satisfies. Second one, associativity. This we have to also check that here the operation is associative, right? So this is also true. What is the next one? Additive identity, right? Additive identity. Does it have additive identity? So what is this means? You have to check for u. What you have to check? U plus v equals to u for all u. Does there exist v or not? Such that this. So let's check. Yes. Yes. Any question? Okay. So we have to check this. Does there exist any v, small v in capital V, such that u plus v equals to u? So means what you have to check, what is the addition here? It's u dot v, right? Equals to u. So for all u in v. So what will be the choice of v for which will be satisfy this equation? So you can take v to the power r, right? 1, which belongs to in v, r plus, right? Positive real number. So then u dot 1, it's u, right? We know. So which imply, so we get a v, right? 1 is the, so which imply 1 is the additive identity. Is this fine? This one? So it has also additive identity. Yes. 1 is the additive identity. Okay. So what is the next property we have to check? Additive inverse, right? So the fourth one. What is this? Additive inverse. So means what we have to check? For u in V, does there exist a V in V such that, so what is the u plus V is the, what is the additive identity? It's 1, right? So u plus V is 1, right? So then what will be this? So you have to check for all, for this we have written. So this we have to check, right? Does there exist a V such that for u in u plus V is 1 or not? This is the additive identity, right? So what is this then? So what is this? U plus V is u dot V, and this is 1, right? So what will be the V, choice of V, which will satisfy this? Can anyone tell? 1 by u, right? So this will be again positive. So take b to the power 1 by u, right? Because u is positive, and so this is also in r plus. So additive inverse is also there. Is the additive inverse. Now what next you have to check? This is the multiplicative identity, right? So this we have checked earlier, that it has the multiplicative identity. Multiplicative identity you have also checked. Multiplicative identity. This is also you have checked. Now what is the next one? Multiplication is associative. Let's check this. Multiplication is associative or not. So what do you have to check? For A, B in R and U in V, you have to check A dot B dot U is A dot B dot U or not, right? This we have to check. So what is this? So let's check A dot B dot U. So A dot B is A dot B because this is the scalar. So AB times U, and what is the scalar multiplication? U to the power AB, right? So this will get this, and now the right hand side A dot B dot U. So what is this? B dot U is what? It's U to the power B. Now what is A dot U to the power B? Is U to the power B to the power A. Now is these two are same for real number? U to the power B to the power A or U to the power AB? These two are not same, right? Always. You can always find AB and use positive such that these two are not same. So which imply multiplication is not associative. So multiplication is not associative, right? So we get that multiplication is not associative. But to become a vector space, multiplication should be associative, right? Oh, where I have written it? Why mistakenly written it here? Oh, these two are the 5 and 6 are here. So these two are question number 3. So what we got, that multiplication is not associative. So B is not a vector space over R, right? So what we have got? So the answer is no, right? Is this fine? So question number 3, we have B is not a vector space over R. Could you give an example? Means what is the example you want, right? Yes. Oh, non-associativity. Okay. So what we have to find, right? So these two are not associative. Means just take U to be some 3 or 2. Take U equals to 2, and what A you will take 2, B took 3. Then what will be the U to the power? AB means U to the power 2 to the power 6, right? And what is U to the power B to the power A? What is U to the power B? 2 to the power 3 square. It is 8 square. Is these two are same? Yes. Okay. Right? No, I think these two are same, right? No, I think these two are same. You can take some different example. Take U to be 3 or 4. So then it become 4 to the power 6, and here it will be 4 to the power 4 cube. What is 4 cube? 64 square, right? Now you will check that these two are same or not, right? These two are same, or these two are same, 64 to square and 4 to the power 6. Yes. Is this same? Let me check. 64 square and 4 to the power 6 in calculator. Just 1 second. Okay. So these two are same. Then multiplication associative here. Is this true? U to the power AB and U to the power A, B to the power A is always same. Suppose if you take this to 3, then 4 to the power 9 still this becomes same. Can you check? Can anyone? Okay. Oh, okay, right. These two are same, right? Sorry. These two are same, right? These two are same. This is again U to the power AB, right? Yeah, these two are same. Right. So this is multiplication again associative. So this is also true. Then what is the next you have to check? Now what remains? What are the other properties? What are the remaining properties for vector space to make it? Yes. Is this so? This is become linear, right? This is distributed. All the properties are satisfied, or any property remain? Yes. What are all the properties? It's for multiplicative inverse. Inverse is not. No, it's multiplication. A dot u. Multiplicative inverse. So then it becomes the vector space, right? So we become a vector space. It satisfies all the condition, right? So it will become then the vector space. Any property left it or not? Let me again check. Commutativity, associativity, additive identity, additive inverse. What are the left? Multiplicative identity. Multiplicative is associative. Multiplication is distributive. We have checked. And multiplication is linear also, right? So V become the vector space, right? Okay, then V will become the vector space. Okay, is this fine? What you are saying, exponential can be multiplied, right? Okay. So now move to the next one. Question number 4. What it is saying? It's saying that let P be a polynomial of degree less than equals to P3R. We have defined earlier. It's the set of all polynomials degree less than equals to 3. So it will be look like a0 plus a1x plus a2x square plus a3x cube. And what is SP? SP is the sum of all the coefficients. And determinant of P is the coefficient for x to the power 0, means a0. So now we have defined for any polynomial, we have defined the P star to be P of minus x. Now you have to check which of the following are the subspace of P3. Right. So let's check one by one. So P belongs to P3 of R, polynomial of degree less than equals to 3. And what is SP? SP is a0 plus a1 plus a2 plus a3. And what is det P? Det P is a0. And what is P star of x? It is P of minus x. Now we have to check this 5 are the subspace or P3 or not, right? So the first one, what is W is? W is all P in P3 such that SP is 0. So to become a subspace, what you have to check? So this is the closed under addition and scalar multiplication. So let's check it. So take any two polynomial P1, and so P1 of x, so a0 plus a1x plus a2x square plus a3x cube, and take another b2 of x, b0 plus b1 of x plus b2 of x square plus b3 of x cube. Now you have to check that p1 plus p2 with the condition, yes, sp is 0 is given, mean what it is given, that a0 plus a1 plus a2 plus a3 is 0, and here also b0 plus b1 plus b2 plus b3 is 0, right? Now you have to check p1 plus p2 is in w or not. So let's check p1 plus p2. What will be the p1 of p1 plus p2? We have defined it. It will be a0 plus b0 plus a1 plus b1 of x, b1x plus a2 plus b2 x square plus a3 plus b3 x cube, right? Now we have to check that what will be this sum. If p1 plus p2 become in w, then s of p1 plus p2 must be 0, right? So s of p1 plus p2, what will be the s of p1 plus p2? So it will be a0 plus b0 plus a1 plus b1 plus a2 plus b2 plus a3 sorry plus a3 plus b3. This should be 0, right? So now here these are all the addition in the real number. So how you can write it? So a0, this you can write a0 plus a1 plus a2 plus a3 plus b0 plus b1 plus b2 plus b3, right? And you know this is 0 because p1 is in w, so this is 0, and p2 is in also w, so b0 plus b1 plus b2 plus b3 is also 0. So we get s of p1 plus p2 is in 0, right? Which implies p1 plus p2 is in w, right? So addition is in the w. Now you have to check the scalar multiplication. So you have to check s of cp, for c is in real number, s of cp1 means cp1 is in w or not. So you have to compute the s of cp1. So what will be the s of cp1? So it will be multiplied by a naught plus ca1 plus ca2 plus ca3, right? All the coefficient will be multiplied by c. Then what you can write? C of a0 plus a1 plus a2 plus a3. And you know p1 is in w, which means this is 0. So this is c dot 0, which is 0, which imply cp1 is also in w. So what is saying that if w, so if p1 and p2 is in w, then p1 plus p2 is in also w, and c dot p1 is also in w, which implies w is a subspace of p3, right? So which implies w is a subspace of p3r, right? Okay, so the first one is true. Now the next one, it is saying w p is in p3 such that sp equals to 1. Now you have to check this. So the question number 2, so w, it's all p in p3r such that sp is 1. So again, as previous, take p1 and p2 as early. p1 p2 is in w as early. So you have to check the SP1 plus P2, right? So what is SP1 plus P2? So this is this, right? SP1 plus P2 is this. So you have to check this. So means this is, we know this is A naught plus B naught plus A1 plus B1 plus A2 plus B2 plus A3 plus B3, which is A naught plus A1 plus A2 plus A3 plus B naught plus B1 plus B2 plus B3. And because P1 is in W, means A sub P1 is 1, right? So this sum A sub P1, what it is, A sub P1, A naught plus A1 plus A2 plus A3. So this is 1. Similarly for A sub P2. So this is 1 plus this is 1. So we get A sub P1 plus P2 is 2, not 1, right? So this is not 1. So which imply P1 plus P2 does not belongs to W, right? So W is not a vector space, subspace. W is not a subspace of P3 R, right? So it's not closed under addition, right? So option number 2 is false. Is this fine? Okay, so let's move to the next option. What it is saying, W all P in P3 such that S P star equals to 0. Question number 3. W all P in P3 such that S P star is 0. So what is P star? P star X is the P of minus X. So means if P1 of X is A naught plus A1X plus A2X square plus A3X cube, then what will be the P1 star of X? It will be P1 of minus X, right? So means it will be A1 minus A1X plus A2X square plus, or it will be minus here. Odd term will be changing sign, A3X cube, right? So now we have to check if two elements, take two elements P1 and P2 is in W. We have to check P1 plus P2 is in W or not. So that for that we have to compute S P1 plus P2 star, right? So what is P1 plus P2? So P1 plus P2. So we know P1 plus P2. P1 plus P2 we have got, right? So what is the P1 plus P2? Write it down just now. P1 plus P2 of X. It will be A naught plus B naught plus A1 plus B1X plus A2 plus B2 X squared plus A3 plus B3 X cube. Now you have to take the star, means you have to replace X by minus X. So then here it will change sign here and here. These two will be changes sign, these two, and then you have to take S, means you have to sum all the coefficients. So it will become A naught plus B naught minus A1 plus B1 plus A2 plus B2 minus A3 plus B3, right? So then what happened? So this you can write A0 minus A1 plus A2 minus A3 plus B0 minus B1 plus B2 minus B3. And you know P1 P2 in W means A0 minus A1 plus A2 minus A3 is 0, and also P2 is in W means this is also 0, so the sum is also 0. So what we got, that S of P1 plus P2 star is in 0, so which implies P1 plus P2 is in W, right? So the addition is in there. So now we have to check the scalar multiplication. So now S of C P1 star we have to check. So that we know it will be multiplied by C and changes the sign. So it will be C A0 minus C A1 plus C A2 minus C A3, right? So what is this? Then C of A0 minus A1 plus A2 minus A3. And this we know is 0. C times 0 as P1 is in W. So which implies this is 0, right? C dot 0 is 0. So which says that C P1 belongs to W. So we got that P1 plus P2 is in W, C P1 is also W for C real number. So W is a subspace of P3, right? Which implies W is a subspace of P3R. Right. So the question number 3 is also, option 3 is also correct. Now the option 4, what it is saying? W all P in P3 such that P plus P star is 0. So question number 4, it's saying that W all P in P3 such that P plus P star is 0. So is this vector space or vector subspace of P3 or not? We have to check. So as earlier again take P1 P2 in W. You have to check P1 plus P2 and see P1 is in W or not. So P1 plus P2, take this plus this P1 plus P2 star, right? You have to check this is 0 or not. So what will be the P1 plus P2 and P1 plus P2 star? So this you know P1. What is P1 plus P2 star? So suppose this is A0 plus A1. So means P1 plus P star, it's given that P1 plus P1 star is 0 and P2 plus P2 star is 0. It's given. So you have to check what is P1 plus P2 star. Okay, this you can check that P1 plus P2 whole star is P1 star plus P2. So means this P1 plus P2 plus P1 star plus P2 star. So hard to check P1 plus P2 star is P1 star plus P2 star. Why this is so? Suppose, so what is this? Suppose P1 of x is this A0 plus A1x plus A2x square plus A3x cube, and P2x is B0 plus B1x plus B2x square plus B3x cube. So then what will be the P1 plus P2 star? P1 plus P2 star of x. So first add, then put x equals to minus x. So it will be A0 plus B0 minus A1 plus B1 plus A2 plus B2 minus A3 plus B3. And what is P1 star plus P2 star? This you check just, it will be again same. So a1 minus a1 plus a2 minus a3 plus b0 minus b1 plus b2 minus b3, and these two are same, right? So we have got that this is same. So now what is this? So p1 plus p1 star plus p2 plus p2 star, and we know as p1 is in w, so p1 plus p1 star is 0 and p2 plus p2 star is 0, means this is 0 plus 0 is 0, which implies p1 plus p2 is in w, right? So addition is closed. Now you have to check the scalar multiplication. So means what you have to check? C dot p1 star is 0 or not. So what is C of p1 star? We know p1 star is 0. So C of p1 star is just C of C of p of minus x, right? So what is this? C of a0 minus a1 minus a0 minus a1x plus a2x square minus a3x cube, and as p1 is in W's, what do you have to check? C p1 plus C p1 star. Okay, sorry. So what we have to check? You have to check that C p1 plus C p1 star is 0 to check, right? This we have to check. So okay, as early you can check C p1 star, C p1 whole star. So what is this? C p1 just compute and then of x, right? So it will be C into a0 minus C a1 x minus plus C a2x square minus C a3 x cube, and C p1 star is of x is also same, right? C a0 minus C a1x plus C a2x square minus C a3x cube. So C p1 plus C p1 star. So these two are C p1 plus C p1 star, right? Because of this. So now take the C common. So p1 plus p1 star, and you know as p1 is in W, so C times 0 as p1 is in W, so means this is 0, which implies C p1 is in W, right? So p1 plus p2 is in W and C p1 is W, so means W is also a vector space. W is a subspace of P3. So the option number 5th, what it is? W, so the P plus P star is 0 is also a subspace. Now the last one, what you have to check? W P in P3 such that determinant of P is 0. This is a subspace or not. So let's check this one, 5th one. What it is? W P in P3 such that determinant of P is 0. So what is determinant of P? determinant of a polynomial, what it's defined, it's the a naught, the coefficient which is if p is like this, a naught plus a1x plus a2x squared plus a3x cube, then a naught will be the determinant. It's defined like this. So we have to check p1 plus p2 is in W or not. So means we have to compute the determinant of this. So we know p1 plus p2, what will be the determinant? It will be the a naught plus b naught, right? So this is p1 and p2 is this b naught plus b1x plus b2x squared plus b3x cube. Then this will be the determinant, right? And p1 is in W, imply a naught is 0, p2 is in W, imply b naught is 0. So these two are 0, which is 0, imply p1 plus p2 belongs to W, right? Because determinant of p1 plus p2 is 0. So W is closed under addition. Now you have to check, is it closed under scalar multiplication or not? So let's check. So for that we have to check determinant of CP1, it's 0 or not. So what will be the determinant of CP1? It will be the C times A naught, right? Just multiply by A naught. So but as P1 is in W, again as P1 is in W, which imply A naught is 0. So this is C times 0 means 0, which imply CP1 also is in W. So addition and scalar multiplication both are closed in W, which implies W is a subspace of P3R, right? So the last option is also correct. So this is also correct. So the only option 2 is false, all the other options are correct. Is this fine? Okay, so now let's move to the next one, question number 5. What it is saying? Pick the choices corresponding to which given a vector u is in the span of the given set. So you have to check u is in the span of S or not, right? Span, what is the span of a set? It is the finite linear combination, right? So first one, what S is given, this is 1 minus 1 1 and 1 0 2. You have to check that u, what is given 2 1 minus 2, does it belong or not belong in the span of S, right? That you have to check. Means, so this is the same as, can we write 2 1 minus 2 as the linear combination of these two? Means sum A 1 minus 1 1 plus B 1 0 2 for sum AB, right? This you have to check. So let's check. Then what will be this side? So just sum coordinate wise. So it will be A plus B minus A and B is 0. It will be A plus 2B. Now equate this both sides. So then what you will get? A plus B is 2 minus A is 1 and A plus 2B is minus 2. So you get A equals to minus 2. From here what you will get? B equals to 2 minus A means 2 plus 1, it's 3. Now check these two satisfy of this or not. So A plus 2B means minus 1 plus 6, right? What it is saying? It's 5, but it's saying that A plus 2B is minus 2, so this is not equals to minus 2. So this is not consistent with the third one. So means there does not exist any AB, right? Because these three equations are not consistent. So there does not exist any AB which satisfies this one. In real number. So what it is saying that, which is mean that U is not in the span of S. So imply U does not belongs to the span of S, right? So the first option is false. Now check the next one. Does U belongs to the span of the R3? This S. Check it is similarly. So we can, so what it is, U is 1, 2, 4, and what is S? 3, 4, 2, 1, 1, minus 1, right? So again write 1, 2, 4 as A times 3, 4, 2 plus B times 1, 1, minus 1 means 3A plus B, 4A plus B, and 2A minus B. So then this is same as, so 3A plus B equals to 1, 4A plus B equals to 2, 2A minus B equals to 4, right? Now you have to solve these three equations. So just subtract first one and second one. 3A plus B equals to 1 and 4A plus B equals to 2. Just subtract these three, then what happens? B will cancel out, minus A will be minus 1, which imply A is 1. Now what will be then B? So B will be, B will be 1 minus 3A, means 1 minus 3, which is minus 2. Now check this A and B are satisfied by the third equation or not. So now check 2A minus B equals to 2 times 1 minus 2. Sorry, it's 2A minus B. I think it's minus 2, right? So this become minus 2 means 4, right? So it is consistent with the last one. So we get, so there exists a solution AB of this three system of equation. So which imply that we can write 1, 2, 4 as 3, 4, 2 plus what is B, minus 2 times 1, 1, minus 1. So which imply U belongs to span of S, right? So this question is correct, option number 2. U is in the span of S. Okay, now let's check the next one. I think this you can check, I'll leave it for you, because this will be similar, coordinate wise you have to check. So let's do it the fourth one. Fourth one, what it is saying? U is x square minus 1 and S, what it is? S is 1 minus x and 1 plus x. You have to check, does U belongs to span of S? So means can we write x square minus 1 as some A times 1 minus x plus B times 1 plus x. So what will then A plus B plus minus A plus B times x plus 0 times x square, right? So but this cannot be because the coefficient here x square, coefficient of the x square is 1 this side and this is 0, but 1 not equals to 0, so there does not exist any AB, right? So which implies there does not exist any AB which satisfies this. So U does not belongs to span of S, right? So then question number 4 is also false. Okay, let me tell you that this will not be there in the span of S. This you can easily check. So the question number 3 is also false. So now check the last one. You have to check again U is in the span of S or not. So the last one, what is U? U is 1 plus x square. And what is S? S is 1 plus x, 1 plus x square. So if U is in the span of S, then U can be written as linear combination of these three. So means 1 plus x square can be written as A times 1 plus B times 1 plus x plus C times 1 plus x square. Now equate the coefficients, so it will be A plus B plus C plus B times x plus C times x square. So what you will get then, A plus B plus C equals to 1, B equals to 1, C equals to 1. So what will be the A then, which imply A will be minus 1, right? So we get the ABC. So U is in the span of S, because all three, from the three equation we get A equals to minus 1, B equals to 1 and C equals to 1. So U belongs to span of S, right? Is this fine? So the question number 5 is true, right? Okay. So now move to the next one, question number 6. What it is saying, let A be subsets of a vector space B, then which of the following statements are true? So the first one, let me do it. If A intersection B is empty, then span of B not equals to span of A, saying that. Can it be happen? So it's true or false, you have to check. So let's take B to be R, and A or B are two subsets. So let's take A to be just 1 and B to be minus 1. Then intersection of A and B is empty, right? They are disjoint. But what will be the span of A and span of B? R, because in R both span R, because if what is the span of A? Span of A means it is all the C times 1 such that C is in R, right? So which is R? And also what is the span of B? Span of B means some C times minus 1 such that C is in R. So this, you get all the real number, right? So this is also R, which implies span of A equals to span of B. So if so what we get, span of A and A intersection B is empty, but still span of A and B are same. So the first one is false, right? Okay, so now move to the next one. It's saying that span of A equals to span of B if and only A equals to B, right? span of A equals to span of B if and only if A equals to B. Means you have to say, so first check this direction. So assume A equals to B. And then span of B equals to span of B, you have to check. This will be because both sets are same, so span of B A, so you can write as a span of B, right? Because A and B are same, so which implies this, right? So this direction is true, trivial. If A equals to B, then span A and span B are same because sets are all the same. Now check this direction. Means assume this. Span of A equals to span of B. Does it imply A equals to B? It's not, right? We have done the first one. A and B are these two sets, but span are the same. So this is not true, right? From the previous, from 1, we can see that we can see span of 1 and span of -1 are same on R, right? But 1 not equals to -1. These two are not, right? These two set are not same. So A not equals to B. So this is false, right? So now move to the next one. What it is saying, A is a subspace of B if and only if span of A equals to A. So let's check. So question number 3, what it is saying, A is a subspace of B if and only if span of A equals to A. So okay, let's first do this direction. Assume span of A equals to A, and you know that it's done in the class that span of A is always, because A is a subset of B, then span is always a vector space, right? And as span of A is always a vector space and A is a subset of B, means span of A is a subspace of B, right? Yeah. Is a subspace of B. So this direction is true. If span of A equals to span A, then A is a subspace of B. Now check the other direction. So means what we have to check? If A is a subspace of B, then span of A equals to A or not. So assume A is a subspace of B. To show span of A equals to A, right? So first note, because A always contains span of A, right? Why? Because any element for as any V in A, you can write some 1 times A, right? This you can write 1 times V, which is in A, where 1 is a real number, right? So which imply B is in the span of A, right? Because this is a means only one element is in linear combination contain only one element. So trivially A is in the span of A, all the elements. Right? Now we have to check the other direction. That so to check span of A is a subset of A. This we have to check. And what is given? A is a subspace of B. This is our assumption. Right? So this we have to show. So you have to show one direction we have done. You have to check the other direction. So now so take any element. So suppose B is in span of A. So if B is in span of A means, what is the definition of span? Means there exists some U1, UK from A and A1 dot dot AK from this R, right? Such that B you can write it as A1 U1 plus A2 U2 plus dot 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 AK UK. So this is the definition of span, right? Because B is in the span, so B you can write it as the finite linear combination of elements from this U1 U2 UK from A and A1 U2 scalars from R, right? And now you know U1 U2 UK are all as U1 dot 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 UK in A, and A is a subspace, and A is a subspace of B. So what is the meaning? Subspace means if U1 is in, so which imply A1 dot U1 is in A, right? Because subspace means scalar multiplication is there. Scalar multiplication property. Right? So which imply dot 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 all the AK UK also in A, right? Because U1 U2 UK in A, so all the scalar multiplication will be there. And as A is also subspace, which implies the sum is also there, right? Plus dot dot AK UK will be there. By addition formula. As A is a vector space, A is a subspace. Right? So imply this is the B, right? So B is in A. So what we have taken? We have taken B from the span of A and we have shown that B is in A. So what is the meaning of this? That span of A is a subset of A. Right? So we have done the other direction also. So first we have shown that A is a subset of span of A, and here we have shown that span of A is a subset of A. So what we have get? Span of A equals to A. Right? So we are done. So this is also true. This is true, right? If A is a subspace of B, if and only if span of A equals to A. Right? Now let's move to the next one. What it is saying? If span of B does not contain a span of A, then A is not contained in B. So let's check this. Fourth one. What it is saying? If span of B does not contain in span of A, then A does not contain in B. So let's on R2 take on R2. Take this, A is 1 0, right, just as R2. So this is 0 0, this is 1 0, and take B to be this 1 0 and 0 1. Take this set 1 0 and 0 1. Then you can check that span of B. What will be the span? You can check that these two vector will span the R2. Span of B will be R2. And what will be the span of A? Span of A, it will be the x-axis, x comma 0. Say that x belongs to real number. So span of B will be the whole R2, and span of A will be the only this x-axis. So let's color it by red. So this is the span of A. Okay. So what we have got, that span of B. So R2 is not a subset of span of A, right? So span of B is not contained in span of A, but A is contained in A. But note that A is a subspace. A, what is A? This is 1 0, right? This is a subset of this. 1 0 is there. And this is B. So A is a subset of B. Span of B does not contain in A, but A is subset of B. So this option is false. Right? Now the last one, what it is saying, if span of A is B and A is subset of B, then span of B is also B. You have to check. So let's check the next, fifth one. What it is saying, if span of A, this is B, A is a subset of B, then span of B is also B. So you have to prove this, right? So first note, A is a subset of B and both are the subsets of B, right? So what will be become? So A is a subset of B and span of A is B, which implies span of A is also contained in span of B, right? And and this is a subspace, right? So let's do it this way. And B is a subset of B. So as B is a subset of B and B is a vector space, so span of B is a subset of B, as B is a vector space, right? As because A is a subset of B and span of B is a vector space, so which will contain in the B, right? Because B is contained in B. So span of B is contained in B. So we get this, span of B is a subset of B. Now you have to check the other direction. To check what it is, we have to check B is a subset of this, we will show span of B, right? Then we are done. Using these two inequality, span of B will be B. So let's check. So take any element from B. So take B from B, small b, and what we know, that span of A is B. So this is the span of A. So what is the meaning of B is in span of A? Means there exist u1, u2, uk from A and a1, a2, ak from R, such that B you can write a1 u1 plus dot 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 ak uk, right? and U1, U2, UK all are A, and A is a subset of B, right? As A is a subset of B, which imply from this that U1, U2, all the UK are also in B, right? So, this U1, U2, UK are in B, and B is like this. So then, B equals to, which imply, B, okay. So does B is in, from here we have to show B is in the span of B, right? So as B is, now what is B? B is A1, U1 plus dot 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 AK, okay, right? So this, where, what is the, where U1, U2, UK are from B, and A1, A2, AK from R. So what is the meaning of this? So B you can write from U1, U2, UK from B, and A1, A2, AK from R. So this is the meaning that B is in the span of B, right? This definition. This will imply this, right? If B can be written like linear combination from the elements from U1, U2, UK from B and A1, A2, AK from R, means B is in the span of B. So you have taken B from the capital B, and you also B is in the span of B, which imply capital B is a subset of span of B, right? So this we have shown, and earlier we have shown that span of B is a subset of B. So combining these two, so span of B is B, right? Is this fine? This one? So what we have got? 5. If span of A is B and A is subset of B, then span of B is B. Means what it is saying, that if span of A is B, then any set which contains A is also the span of that set is also is B, right? So question number 6 is done. Okay, now move to the next one. This is the last question for today's assignment. So this is the question number 7. What is saying? Let T be an infinite subset of distinct vectors in R2. Which of the following statements are true? There always exist 3 distinct vectors in T which span R2. Right? So T is is this correct or not? T is infinite subset of R2. So let's take T to be this. Suppose वो क्लोज हो गया है लेकिन इन्होंने इंफॉर्मेशन हटाया नहीं. So you have to check. There always exist 3 distinct vectors in T which spans R2. So suppose say that X belongs to R. So this is the infinite subset, right? Because this is the real axis. So this has infinite number of points. So this is the infinite subset. Now take any 3 distinct vector. Suppose take 1, 0. Then there always exist 3 distinct vectors which span R2. But this cannot span R2, right? R2, to span R2 you need, so this is R2. So what will be the span of T? Can this span? What is the span of T? So span of T will be C times x comma 0. So that x in R and C is in R, right? So this is again some y comma 0, right? Or y is in R. So this is again t, because so this is not R2, right? So there always exist three distinct vectors in T which spans R2. This is not the case, right? T is a vector space, so span of T is again the same, and this is not R2. So take any three vectors, it cannot span R2. So there does not exist any three distinct vector in T which spans R2, right? So the first option is false. So now check the next one. What did it say? There exist three distinct vectors in R2 which does not span in R2. So what did it say? Question number 2. There does not exist three vectors in R2 which does not span R2. Sorry. This is R2 0 0. Saying that there exist, what is the question? There exist three distinct vectors in R2 which does not span R2. So what three vectors you will take? Take the any three vector in the x-axis, because this x-axis is a subspace of R2. So if you take any vector space, it will again in R, this x-axis. So it will not span R2, right? So take these three vector. So take 1 0, 2 0 and 3 0. Then you can check, suppose take A to be these three. Then what will be the span of A? Then span of A, it's the x-axis, right? X comma 0, say that x is in R. And this is not that. So there exist three distinct vectors in R2 which does not span R2. So the option number 2 is true. So now move to the third option. What it is saying? The linear span of T is R2. So again 3, what it is saying? T is any infinite subset. It's saying that span of T is R2. It's saying. Does it true? No, it's not, because you can take any vector in the x-axis. This is the x, suppose take t equals to this. Again the same example, x comma 0, so that x belongs to R. Then span is not, right? Then span of t, we have showed that span of t is y comma 0 something, so that y belongs to R, right? So this is again not R2. So the question number 3 is again false. Option number 3. The linear span of T is not R2. So this is not always true, right? Now move to the next option. The linear span of T cannot be 0. So what it is saying? Option number 4. As saying that linear span of T cannot be 0. What is T? T is an infinite subset of Earth, as T is a infinite subset, right? Infinite subset of Earth means it will contain at least one element. So which imply there exists AB belongs to T, which is non-zero, such that AB is means at least one element, means T is non-empty, right? As T is non-empty, so which implies there exists at least one element. So what will be then span of T? So span of, if you do the span, then at least this element will be there, right? AB will belong in the span of T. As T is infinite, at least one element will belong in the span of T, which imply span of T can't be zero. Span of T is not zero, right? So it is always non-empty. If T is non-empty, then span of T is always non-empty. So the last option is true. The linear option, span of T cannot be zero. Fine. Okay, so this is the last question. Okay. Okay, any question? So assignment 1 is over. Any doubt from the assignment 1? Yes. So if not, then can you provide the solve? Yeah, I will. Yeah, I will upload it in the Google Sheet. There in the website, you can find it. I will share this note also, and the video recording you will also find. Okay. So let's end the meeting. Okay, bye. Okay. So let me stop the sharing.